Hello everybody, welcome into another lesson. So today we are going to graph polynomial functions. So when we graph polynomial functions, the first thing we want to talk about is end behavior. So if the degree of the polynomial function is an even power, such as 2 or 4 or 6, what have you, and the leading coefficient is positive, then the graph of that curve rises to the left and rises to the right. So for example, I have graphed here f of x equals x to the fourth. It looks very similar to f of x equals x squared. And if we did x to the sixth or x to the eighth or x to the 10th instead, it would have a very similar shape. It would rise to the left and rise to the right because it's an even power polynomial and the leading coefficient is positive. Now, on the other hand, let's say f of x equals negative x to the fourth. So this time we make the leading coefficient negative. So let me fix this here. So if for end behavior, if the polynomial again is an even power function, but the leading coefficient is negative, the graph will fall to the left and fall to the right. So let's do f of x equals negative x to the fourth. You would get a shape roughly like this. And if we did f of x equals negative x squared or negative x to the sixth or negative x to the eighth, you would get a parabolic looking curve like this. It would fall to the left and fall to the right. So that's end behavior for even power polynomials. Now let's move on to some odd power polynomials. No, actually, that's correct. All right, so now, if you have an odd power polynomial, so we're going to do f of x equals x to the third. That's an example of an odd power polynomial, and your leading coefficient is positive, which we have here. The graph will fall to the left but rise to the right. So let's demonstrate that with f of x equals x to the third. Alright, so here's the graph of x to the third. From its central point at 0, 0, it's falling to the left. The further left you go, it's falling, but the further right you go with x, it's rising. So if it's an odd power polynomial and the leading coefficient is positive, such as with f of x equals x to the third, the graph will fall to the left and fall to the right. The same would be true if you did x to the fifth or x to the seventh, x to the ninth, what have you. You would get a very similar curve. Now, on the other hand, let's talk about negative leading coefficient with an odd power function. Alright, so if you have an odd power polynomial such as f of x equals negative of x to the third, and the leading coefficient is negative, such as seen here, then the graph rises to the left and falls to the right. So let's demonstrate this one. So as you see with this graph, since you have an odd power polynomial and your leading coefficient is negative, your graph is rising the further left you go, and it's falling the further right you go. So that's general end behavior. Now we're going to graph some polynomial functions. We're also going to get into multiplicity of zeros, what those mean. We're going to graph, of course, the zeros themselves, and the y-intercepts and multiplicity of zeros, talk about what those mean, and all that stuff. So let's say we have f of x equals x to the third minus 9x. You're given f of x equals x to the third minus 9x. Well, it's important to apply the leading coefficient test first. We have an odd power, right? The degree is 3. This is an odd power. So, and you got an even leading you got a positive leading coefficient, so it's going to fall left, rise right. So this graph falls to the left, rise to the right. Now, another thing that might help you is to consider the y-intercept. Of course, that's when x equals 0, you would get 0 for y. So you have a y-intercept at the point 0, 0. As it so happens, we're going to see in a second that's also the x-intercept. And that's the very next thing we're going to talk about, x-intercepts. This one can be solved simply by factoring. So if we set that x to the third minus 9x equal to 0, this would factor into x times x squared minus 9 equals 0, which again would factor into x times x plus 3 times x minus 3 equals 0. So you'll have x-intercepts at both plus and minus 3, 0. And then you'll also have one at 0, 0, which is already plotted. So let's plot negative 3, 0. Let's plot positive 3, 0. All right, so we have all the zeros and the y-intercepts plotted. Now, notice that each of these is to the first degree, each of these factors, right? That's called your multiplicity, the degree it's raised to for your factors. So if it's an odd multiplicity means graph crosses x-axis at those intercepts. So the graph will actually cross through the x-axis at those intercepts if you have an odd multiplicity. If you look at x, it's raised to the first power, so it's going to cross through the x-axis at x equals 0. If you look at x plus 3, you have it raised to the first power. That's an odd multiplicity, so it'll cross through the x-axis at x equals negative 3. And then again, you have x minus 3, where that's raised to the first power, odd multiplicity, so it'll cross through the x-axis at x equals 3. Now, had you had an even multiplicity, like you had one of these raised to the second power or something like that, if you have an even multiplicity, it'll only touch the graph. It'll only touch the x-axis at that point, but not cross through it. So odd cross even touch. You can remember it as if you even touch. That's the best way to remember your multiplicities. Then we have to talk about turning points. So you'll notice the graph will turn from increasing to decreasing at absolute maximum and minimum values. Okay, well, the degree of the equation, you take the degree of the equation, which is 3 minus 1. So it's always the degree of the equation minus 1. In this case, you could have at most 2 turning points. You have at most 2 turning points. Now, had this just been something like x minus 1 to the third, you would only have 1 turning point simply for the fact that it's 1, 0 repeated 3 times. And it would be basically the same as the graph of f of x equals x to the third shifted to the right 1 unit. That's all that would be. But if you have more than 1, 0, then odds are in your favor you're going to have that full number of turning points. The most any graph can have is the number of degrees of the polynomial minus 1 for your turning points. Alright, so with all this information, let's go ahead and graph this. We know it falls to the left but rises to the right. And to top it off, it's going to cross through the x-axis at -3. So your graph's going to start out looking something like this. It doesn't cross again till 0. So if it goes through, it's going to go above the x-axis. It crosses through at 0. And then it's going to go down. And then it crosses through when x equals 3 and it rises to the right. And you see you have your 2 turning points somewhere in the second and fourth quadrants. So you have 1 turning point and a second turning point where you have an absolute, where you have a maximum and a minimum value. Those are your turning points. So this graph of f of x equals x to the third minus 9x would look about like that. And I got more. Now there could be problems you have to do synthetic division for. You will sometimes have that. So where you could find your 0. Alright. F of x equals x to the fourth minus 4x squared. So you have f of x equals x to the fourth minus 4x squared. Well, let's start out with a leading coefficient test. It's an even power polynomial raised to the fourth power, right? And you have a positive leading coefficient, so it'll rise to the left and right. So this graph rises left and right. So now we know the immediate end behavior. Let's find the y-intercept. That's when x equals 0. You'll have a y-intercept at the point 0, 0. So let's plot the y-intercept. Okay, now let's find the x-intercepts by setting this function equal to 0. So take x to the fourth minus 4x squared, set that equal to 0. Well, we could solve this by factoring again. So this will factor into x squared times the quantity of x squared minus 4 equals 0, which will further factor into x squared times x plus 2 times x minus 2 equals 0. Alright, so our zeros, x equals 0, but notice that x is raised to the second power. So x equals 0, that'll be multiplicity 2. And then x equals both plus and minus 2 with a multiplicity of 1. So your zeros are, of course, at 0, 0, and then you have negative 2, 0, and positive 2, 0. Now, here's the thing. If you look at negative 2, what's true? It has a multiplicity of 1, right? What does that mean? it's going to cross through the x-axis because it has odd multiplicity. So we could say it crosses, and then it's the same when x equals positive 2, so it'll cross the x-axis at both plus and minus 2, 0. But look at x equals 0. It has a multiplicity of 2. It has an even multiplicity, which means it's only going to touch the x-axis at 0, 0. So yes, it'll touch it, but it won't cross through it. So with all that information and knowing the end behavior, let's graph this function. So we know it rises to the left and right. So you'll start out with something like that. Oh yeah, another thing, this is a fourth degree equation. So turning points take the degree of the equation, in this case, which is 4, subtract 1, you could have at most 3 turning points. Alright, so that'll help us draw this graph. So we know it crosses through at negative 2, 0. Go to 0, 0, it's only going to touch. So here's it touching 0, 0, but it does not cross. Because then it comes back around without crossing the x-axis there. Then it goes through the x-axis at x equals positive 2. So you have it rising to the left and to the right, crossing through x equals negative 2 and x equals positive 2, and only touching the x-axis at x equals 0. And notice you have 3 turning points. You have one at a minimum value, another minimum value, then you have one at a maximum value. So you have a total of 3 turning points with this graph. Alright, got some more. Not mean to kick that. You know, I think that might work actually. That's okay. Alright. Hold on, let me recenter this. This is going to drive me up the wall. There we go. Best I can get it. F of x equals x to the third minus 3x squared. So we have been given f of x equals x to the third minus 3x squared. Well, let's apply the leading coefficient test and determine the end behavior of the graph. So it's an odd power polynomials to the third power. Your leading coefficient's a positive 1, so that means your graph is going to fall left and rise to the right. So that's an important piece, knowing your end behavior. Now let's find the y-intercept. Again, that's going to be when x equals 0. So you'll get a y-intercept at the point 0, 0. So we can go ahead and plot that point, 0, 0. Alright, now let's find the x-intercepts. So set that function equal to 0. So x cubed minus 3x squared equals 0. This would factor into x squared times x minus 3 equals 0. So notice something. You have x squared, which means you have x equals 0 with a multiplicity of 2. That counts as 2 zeros, actually. And then x minus 3 would give you x equals 3 with a multiplicity of 1. So what does all this mean? Well, that multiplicity of 0, that 0 multiplicity of 2, it's an even multiplicity, meaning it'll only touch at 0, 0. So it touches at the point 0, 0. And then x equals 3 has an odd multiplicity of 1, so it'll cross through the x-axis at the point 3, 0. So let's plot 3, 0 right here. Okay. So again, we know it falls to the left and the right. Oh yeah, turning points. So for turning points, take the degree of your equation, which in this case is 3, subtract 1 from that. The maximum number of turning points you could potentially have is 2. So bear in mind now, zeros in x and y intercept both. It falls to the left, rises to the right, and at 0 it doesn't cross, it only touches. So let's start graphing. So of course it's going to go further left, falling to the left. Now it doesn't cross, it only touches. So you're going to come down like this and then come up like that through x equals 3. Since it's got a multiplicity of 1 and it's an odd multiplicity, it'll cross through. So your graph would look something like this. You have 2 turning points at a maximum value and a minimum. So that's roughly what the graph of x to the third minus 3x squared would look like. Okay. F of x equals negative x to the sixth plus 7x to the third plus 8. So f of x equals negative x to the sixth plus 7x to the third plus 8. Well, let's apply the leading coefficient test. This is definitely an even power polynomial because it's to the sixth power, right? But you have a negative leading coefficient. That means it's going to fall to the left and right. So it'll fall left and right. Okay, now, what else do we have? We're going to also want to find the y-intercept. That's when x equals 0. Well, you have a y-intercept at the point 0, 8. So let's go ahead and plot 0, 8. That's all the way up here. All right. Now let's solve for the x-intercept. So take that function, set it equal to 0. So negative x to the sixth plus 7x to the third plus 8 equals 0. Which would end up turning into, at this time, factor out a negative 1, that would turn into x to the sixth minus 7x to the third minus 8 equals 0, which would factor further into x to the third plus 1 times x to the third minus 8 equals 0. So now you just have the factor that is a difference of a sum and difference of cubes for each one. Well, when you're graphing, we can't really graph the imaginary values. You can factor this further and treat it each as a sum and difference of cubes. So you would literally get, if you took x to the third, set it equal to negative 1, you would get that x equals negative 1. And then you would have x to the third equals 8, which would give you that x equals 2. Both of these have a multiplicity of 1. So they're going to cross the x-axis at negative 1, 0 and at positive 2, 0. All right, so it falls to the left and right. Now let's talk about turning points. The number of turning points, again, is the degree of your equation. So 6 minus 1 That's the number of the maximum turning points you could have is 5. You may not have all 5, but you very well could. Now this falls to the left and right, and it crosses through the x-axis at x equals -1. So let's start graphing here. Actually, I think it's going to be a little bit different than that. So let's see. So your graph is going to look a little bit different because those imaginary values still kind of impact your turning points, but they're not going to, of course, be zeros. But you see ultimately it falls to the left and to the right, and it crosses through the x-axis at all of those points. So yes, you have a bit of a mess there, and this also proves you may not have the full number of turning points, but you may end up having up to 5. Doesn't mean you'll have all 5, but you could have up to 5. All right, a few more. All right, f of x equals x to the 5th minus 4x to the 3rd plus 8x squared minus 32. All right, so we have f of x equals x to the 5th minus 4x cubed plus 8x squared minus 32. Let's apply the leading coefficient test and determine the end behavior. So the degree of your polynomial is 5, and you have a leading coefficient that is positive 1. So this is going to fall to the left and rise to the right. All right. So now let's find the y-intercept. That's when x is 0. You'll have a y-intercept at the point 0, -32. Let's make every y unit worth 4. So we'll come down here. This would be our 0, -32 right here. Okay. Now, let's go ahead and solve for our x-intercept. So set this function equal to 0, that x to the 5th minus 4x to the 3rd plus that 8x squared minus 32. Set all that equal to 0. We can factor by grouping. So x to the 5th minus 4x to the 3rd, you factor out a common x to the 3rd. That would leave you times x squared minus 4 plus then an 8 times x squared minus 4 would equal 0. So this would factor into x squared minus 4 times x cubed plus 8 equals 0. So this would turn into x plus 2 times x minus 2 times another x plus 2 times x squared minus 2x plus 4 is equal to 0. Well, notice we have x plus 2 occurs twice. So this would finally break down into x plus 2 quantity squared times x minus 2 times x squared minus 2x plus 4 equals 0. That is the full factorization. Well, that far right factor, that quadratic factor, that x squared minus 2x plus 4, we know there's going to be no real solution. You're going to have two imaginary solutions, so we don't even consider that. But you have, if you take that x plus 2, it has a multiplicity of 2. So x equals negative 2 with a multiplicity of 2. Then x equals positive 2 with a multiplicity of 1. So when x equals negative 2, which we'll plot negative 2, 0. Alright, so it's going to have a multiplicity of 2, which means it's only going to touch there. It's not going to cross there, it'll only touch. Now when x equals positive 2, on the other hand, it has a multiplicity of 1, meaning that it's actually going to cross the x-axis there. So let's talk about turning points also. Since this is a 5th degree polynomial, you subtract 1 from the degree of your polynomial. That means at most you could have 4 turning points. So with all of this information now, let's put this graph together. So it falls to the left. So left of x equals negative 2, it's going to fall. And it only touches at x equals negative 2, meaning it doesn't cross, so it'll come down again about like that. And you'll get something like this. So here's the graph with your 4 turning points. You have 2 maxes and you have 2 mins here. You have 4 turning points. So this is roughly what the graph of x to the 5th minus 4x to the 3rd plus 8x squared minus 32 would look like. It looks kind of cool, but that's what you would get. So I think we'll make that it for this lesson. Next lesson, we're going to go into complex numbers. We're going to talk about imaginary numbers again. So I hope everyone has a great night. Take care.